So now we have the last talk for this parallel session by Giuseppe Bogna, who is going to discuss amplitudes and celestial OPEs around curved backgrounds. Go ahead.
Okay, thank you. First of all, I want to thank the organizers for giving me the opportunity to give this talk. And today we'll talk about amplitudes and celestial OPEs around curved backgrounds. I will base this talk on this series of papers and work in progress, in collaboration with Tim, who's in the audience, with Simon Hoverin, Lionel Mason, and Atul Sharma. Let me first begin with some motivation. So, we want to study scattering around non-trivial backgrounds, basically because it's a very interesting and very hard problem. So, this is to say that we know a lot about scattering on flat space, where we basically have a formula for the S matrix at all multiplicity and at all MSV degree. But we know much less for scattering around non-trivial backgrounds. And yet, this kind of problems is actually very important for many interesting applications. So, for example, you could use it to study phenomenological applications, such as nonlinear QED, identical light collisions, gravitational waves. But it is also very interesting for more theoretical applications. For example, there are a series of work by Tim and collaborators on classical physics and all of data in terms of this kind of amplitudes. And they can also be used to see whether the known techniques that we have for amplitudes around trivial background can actually be extended or not, or modified on trivial backgrounds. For this audience, probably the best application is instead the fact that celestial holography aims to describe quantum gravity on a generic asymptotically flat space-time. So the basic data for curved space-time is actually given by amplitudes on non-trivial backgrounds. So this is the plan for today. I will start with a definition of amplitudes on curved backgrounds, and I will also give some more technical remarks on how we actually compute them. Then I will apply these techniques to show you how we constructed the gluon amplitudes around self-dual dion and their gravitational cousins, so gravitational amplitudes around self-dual top knot. I will comment on how we can use these amplitudes to derive the gluon OP and the graviton OP around this kind of backgrounds. And finally, I will comment on, I will discuss my new work with Simon on the celestial chiral algebra of the Peterson metric. Okay, so as I was already saying many times, we want to study scattering around backgrounds. We consider today strong and self-dual backgrounds. You all know what it is, a background. It is just a fixed, non-dynamical solution to the classical equation of motion. But today we want to consider a background to be both strong and self-dual. By strong, we mean that we essentially want to treat it non-perturbatively. So we want to find amplitudes that are exact in all the data defined in the background. And by self-dual, we just mean that the background satisfies the property self-duality equation. So it is either self-dual, the field strength is self-dual in gauge theory, or the Weil tensor is self-dual in gravity. In this framework, amplitudes are usually defined by the perturbation formalism, which states that a scattering amplitude is given by a multilinear piece of the initial action. We use this definition instead of the classic S matrix element because it can be shown that around a generic background, usually you can't define this matrix because there are phenomena such as absorption, which prevents you from the definition of the S matrix element. On the other hand, this definition is robust. It can be done on any background. And more importantly, when this metric actually exists, then the two definitions agree. Now, this is still very hard. I mean, I told you how to define the amplitudes, but the computation of them is still very difficult on a trivial background, basically because as soon as you turn on the background, then the problem becomes highly nonlinear. And here comes the self-duality assumption to help us. Basically, every time there is a self-dual background, you can invoke twistor theory and try to use it to essentially compute the amplitude. We already saw twistor space a number of times in this conference, so I'll be very quick in this discussion here. What is just important to us is that twistor space is a complete threefold that allows us to essentially recast physical problems in terms of complex holomorphic geometry on twistor space. And so for us, we'll just think of twistor space of this complex threefold, where space-time points are given by holomorphic twistor lines, which are just copies of the Riemann sphere holomorphically embedded in twistor space. Then once you start talking about the complex structure of twistor space, you can define a space-time self-dual metric, which is related to this complex structure. Similarly, a self-dual gauge field is given by certain holomorphic vector bundles in twistor space, as was as Tim was mentioning yesterday, more or less. And once you define the complex structure and the holomorphic bundles in twistor space, you can start talking about scattering states. So solutions to the linearized equations of motion in space-time corresponds to the cohomologies of the relevant Dolbolt operators in twistor space. And once you want to compute amplitudes, you can construct the MHV generating function of the gluon and graviton amplitudes as some specific non-local operators on twistor space. Let us see how this works in the case of the self-dual dion. We consider this background gauge field on space-time. dt over R is an electric part, a little a is a magnetic monopole. The overall gauge field is self-dual, so it has a nice description of twistor space. And if you run the twistor construction, you can immediately define the following set of states. These are solutions to the Laplace equation coupled to this background, and they depend on basically a choice of annual momentum, on the direction of the celestial sphere associated to the undotted spinor, and on the stereographic coordinates on the celestial sphere. Notice that these states are exact, and this is basically what I was discussing before with the definition of strong background. So the charge here in the state appears in the exponent, so the states are in a sense non-perturbative in the background, and we want this feature to essentially talk about the strong scattering. There is a similar story for other elicities, which are relevant for the construction of gluon states. And so with those we can actually start computing the gluon amplitudes. So we consider the Chalmers and Siegel representation of the action for EMEs. So we consider a wave action described in the circular sector with the format with a trace B square operator, which gives us full EMEs up to the topological term. And the lift of the last operator to twistor space is actually what generates the MHP amplitude. As I promised you, it is an local operator in twistor space, and the B1 and B2 basically encodes the two negative elicity gluons. The expansion of this operator in twistor space gives you then the MHP amplitude for gluons. And if you do this, you can first find a very nice and complex expression for the 2-point amplitude, which depends on basically the charges, the energies, and spinor elicity variables of the gluons. And notice that you still have energy conservation because the background preserves the translational symmetry around the time-like direction. But interestingly, you can also write down a nice formula for the 3-level gluon MHP amplitude at all multiplicity, which is the following one. It is very similar to the Parker-Taylor formula, which is given in the first line. But instead of having a momentum conserving delta function that you expect for scattering of flat space, you get the following single space-time integral at all multiplicity, which again depends on the charges and on the momenta of the gluons. With this formula, as an application, we can construct the celestial OP around the self-dual dion, and this is equivalent to the computation of the homomorphic splitting function. From the amplitude, we can derive this splitting function, and we actually found it is the same holomorphic splitting function that we have on flat space. So we discovered that the gluon OP is actually deformed by the self-dual dion, and this is in agreement with the previous work that appeared last year on two-sided monopoles. Now, let us consider a similar problem, and instead of scattering gluons in the presence of a dion, we are now considering gravitons scattering on top of a self-dual top-down metric. We chose to work with this metric, so the self-dual top-down metric, because first of all, it is self-dual, so we know how to describe it in twistor space. Second, it is a toy model for physical black holes. This is because This metric, infinite signature, acquires both an horizon and a singularity. So we can think of it as basically a half of a real black hole like Schwarzschild or Kerr. At the same time, it's still integrable because it's dual, so we can say much more than what we know about scattering on giant black holes. So, for example, this space is a line bundle over the total space of this vibration, and basically applying the same twistor sigma model that Tim was mentioning yesterday, we can actually recast the gravitational MHV amplitude at the level in terms of a correlator of a certain kind of 2D CFT, which is not really important to see explicitly in this slide because it is a bit long. But we do know how to compute this correlator, and the end result is actually very simple again. So at 2 points we can be very explicit and just state a formula for the 2-point amplitude in just a line. What is even more interesting is that we can do the same at MHV degree at any multiplicity and write down the following very convex formula for the gravitational isometrics at this MHV degree. We still have to explore this formula further, but we expect that the gravity on OP is also on the formula in the presence of this of the subdelta metric. So, in the final part of the talk, let me just turn to non-trivial deformation of the chiral algebras. We saw yesterday in Bean's talk that a nice way to deform the chiral algebras is by turning on a cosmological constant. Here we do a bit more. So we both turn on a cosmological constant and we basically pair it up with the self-dual top-knot metric. There is a metric known as Petersen metric which basically does this job for us. So you can see from here that it is essentially the self-dual top-knot metric with this factor here depending on the cosmological constant. It is self-dual, so it is a description of twistor space, and even more interestingly, it basically includes all the known examples that have been studied in recent years in celestialography. So I already mentioned self-dual top-knot and the DS4, but it also includes the Cauchy-Anson in a specific limit of on the space parameter, and it also includes a non-compact version of CP2, which is conformally equivalent to Born space. Now, from twistor space, we know that the celestial chiral algebra arises as basically the Poisson bracket of O2 valued Hamiltonians. We can use it to conjecture the following formula for LW1 plus infinity. And basically, my work with Simon, we show that this is a nice deformation of LW1 plus infinity, which satisfies the Jacobi identity, and more importantly, it reduces to the all known deformations of the LW1 plus infinity that already have been studied in the literature. So ADS4, as Bean was mentioning yesterday, Cauchy-Anson, and in the case of self-dual top-knot, we also found no deformation. There is still a lot to do, so we want to first prove from first principle the claims that I was mentioning today, so basically the gravity on OP and self-dual top-knot. Next, today I only talked about MHV scattering, but it would be nice to extend this discussion to all MHV degree scattering. And if we are able to do so, we might even be able to resum the amplitudes on self-dual backgrounds to actually say something on non-self-dual backgrounds. So, for example, physical black holes and graviton scattering on top of them. Finally, it might be nice to construct correlators around the Petersen metric and to also see whether we can embed these considerations into some top-down constructions in twistidolography. Thanks.
Okay, so we have plenty of time for questions.
Thanks, Giuseppe. I have a couple of super naive questions about your Petersen chiral algebra. Okay. So, can you just talk me through the mode numbers here? So there's
yes, this is just one of the brackets that we have, because basically the form of the generators depends on the parity of I and j.
Yeah, I was going to ask why it looks like something needs to be even here.
It need not. There is also a bracket for 2i plus 1, 2j plus 1, but I didn't stick in the slide.
And how did you guess this?
Yeah, okay, so we looked at this metric, we looked at twistor space. it's a bit difficult.
So you know the twistor description of this.
Kinda. We know.
So
it
I'm aware that it's in Peterson's thesis.
yeah,
in
we
some
know it
sense.
in the Czech language. It's a bit of a mess.
Yeah.
But we kinda know the symmetries of the twistor space because it has a description in terms of the, the spinning metric, the spinning top description of it. So basically, we guessed the Poisson bracket in terms of holomorphic coordinates, which we found. And with that, there is not much more that we can do.
And I guess you have as data points the limits when various parameters.
Yes,
switch
exactly,
on.
exactly.
Okay. And
it is a bit weird because it is similar to the description of the twistor space for studio top nut, but the details are a bit messier because of the cosmological constant.
well, this is like a super naive question, but you mentioned this fact that you'd hope that this family could be described by a kind of line
Yes.
defect, and for self-dual Taub nut, we know that line defect is somehow off the twistor space.
Yes, exactly.
But,
But it is in twistor space. When
exactly, when you switch on the
cosmological
cosmological constant, it's on the twistor space.
Yeah, exactly.
Okay. But you still think it's wrapped on the lambda equals 0
Yes,
line?
yes. Because, basically because the subdual nut limit arises exactly in that way.
Okay.
And also because if you do a conformal inversion, you exactly land on the Eguchi-Hanson
I was just going to ask how
metric.
this gets you Eguchi. But it's some large lambda limit that gets you Eguchi-Hanson. So the
Yes,
roles of mu
exactly. And there's
lambda
also
on
an
the
inversion
twistor
on
space.
space-time, which basically exchanges lambda mu's on twistor space.
Gotcha. Okay, cool. Thanks. Sorry.
All right. Thanks for the nice talk. So I had a question about your self-dual black hole amplitude. How does it compare to amplitudes for non-self-dual black holes, rotating Kerr amplitudes that people have? They have sort of good control over the 3-point and maybe guesses at higher points for the same helicity.
We still want to do those checks at 3 and 4 points. At 2 points, we found agreement, if I recall correctly, right?
Yeah. Okay.
It is a bit difficult to...
2 points means 4 points in normal
Yes, exactly.
Okay.
I mean,
Field theory.
usually people don't talk about 2 points,
Okay.
but if we found the same structure with the Newman-Chain shift and basically
If
the
you took
maximum
a
spin.
perturbative limit of this guy, you'd be trying to compare with the 2 gravitons and kind of 2
Right.
dionic type.
I guess my follow-up question is: Can you prove that they should be the same, and therefore prove what this amplitude should be for the non-self-dual black hole?
Not yet, I think.
You can do that.
Not yet.
Not yet. Okay, but eventually.
We're trying to.
Okay.
Any more questions?
Maybe it's a stupid question, but about your OPE, so there is this observation that you can have failure of associativity of OPE because of some anomalies in twistor space. Do you see some
We don't see
things?
them here.
You
Like
don't
the OP is exactly the same, so there are no...
And for gravity is...
For graviton, we still have to check it from the amplitude, but we know that it is on the form from the Pedersen metric discussion. So we expect that this... What is it? We expect that this amplitude actually gives the same graviton OP that we have on flat space, but we still have to see it explicitly.
So these are tree level computations in twistor space.
Yes, exactly.
Yeah,
So you
we
can be
need to...
sensitive to
Yeah,
this
I know.
anomaly.
There are no more questions. I don't see any. Let's end.